Welcome to this video in the Nomenclature unit. This is 5.1, where today we are going to begin our journey into Unit 5, Nomenclature, Formulas, and Naming. In today's video, we're going to break down the parts of a formula, discuss how to count atoms in a formula, introduce the naming rules for monatomic cations and anions, introduce the naming rules for polyvalent ions of your transition metals, and all of that will be done on your companion worksheet. So if you haven't already done so, grab that companion worksheet, download it and print it, have your chemistry notebook handy, have your writing utensil at the ready, and your periodic table and CsRT available for reference. We got a lot to do today, so let's get going. The first thing we're going to hit on in this video is discussing what a formula is. And of course, you are going to recognize formulas from using them in biology, but what a formula does is tell us the type and the number of atoms that are present in a compound. And here you can see formulas for two popular molecules that you remember from biology class, carbon dioxide and glucose. If we break down what is in a formula, all formulas are going to include element symbols. Those are the capital letters that you see here, and each capital letter represents a new element in your formula. Our formulas also have little numbers that are to the right of our elements. Those are called subscripts. And what a subscript is going to tell us is how many of each atom are present in the compound. What do we use all this for? Well, we use it for a little bit of bookkeeping, where if we look at a formula, we need to know how many atoms total are in the compound. So let's try breaking down these three compounds that are here and make sure you can count the number of atoms that are present. In this first one, I have a sodium atom and I have no subscript, which implies that there is one. So I'm going to do my bookkeeping and say one of those. And now I see a chlorine with no subscript, and that implies one also, so that is one chloride. And if I take the total of those, I have 2 atoms total in this formula. Moving on to this next one, I have a calcium atom that's here, no subscript, so that gives me 1. And of course, you can do your bookkeeping on top too. Some people choose to do that. I have 2 chloride ions that are here, so that gives me 2 of those for a grand total of 3 atoms. Looking over at this is an H2O2. And I have 2 hydrogens that are here, plus these 2 oxygens that are there for a grand total of 4 atoms. These are really easy to get your total of the atoms, but of course, it's going to get harder as we go. But let's make sure we've mastered this skill ourselves. To do so, pause the video now and then total up the sum of the atoms in these 3 compounds. Then unpause the video when you are ready for the answer and see how you did. Okay, if you did this correctly, we should have gotten 7, 3, and 8 atoms respectively. If you did anything wrong, make sure you go back, rewind the video, and figure out where you may have erred. And then once you're ready to move on, let's hit the next topic. Our next topic builds on what we just did, but adds an element to the formula. And that element is called a coefficient. A coefficient is a whole number that is placed in front of the compound formula or the element symbol. And here you can see we have added 8 in front of the carbon dioxide or the sodium atom. And essentially what the coefficient is going to do is tell us how many of each molecule, if we're dealing with obviously a compound or element, will be present in a formula. So if you want to think about this like math, the coefficient will effectively multiply the number of every element in the formula to get the total number of atoms present. With this example here, you know you do order of operations, which has your parentheses happening first. That gives us 4 that are here. And then we are multiplying these 4 atoms that are there by 8 to give us a total of 32 atoms. If we are looking at this in terms of a real formula, well, you got to now first figure out how many atoms are in the ammonia example that we are seeing here. Well, let's do some bookkeeping. We got 1 N and we've got 3 H's. And let's put those in parentheses and multiply the whole thing by 8. So once again, it turns out to be 8 times 4, giving us 32 atoms. So it is important to not only use the bookkeeping skill that we had in the prior segment of this video, but also remember your order of operations in math and what you do with parentheses. So now it's your turn. Let's look at the following formulas and coefficients and count how many total atoms we would have. Pause the video now and then unpause the video when you think you've got an answer. All right, if you did this correctly, we should have gotten 28 atoms, 18 atoms, and 24. If you did make any mistakes, rewind the video and figure out what you may have done wrong. And then when you're ready to go, let's continue. The next thing we have to add into our counting of atoms is what happens when you have parentheses and polyatomic ions. And you will see parentheses when we have more than one set of polyatomic ions in the formula, like we do with this example down below. So how do we use parentheses in these formulas? Well, the subscript to the right of the polyatomic ion that we see only will affect the count of the atoms that are in that parentheses. So we're talking about this subscript to the right basically says I have 3 nitrate ions. And it's like having NO3, NO3, and NO3 all at once. And what you really have to do is count the atoms that are in between these parentheses first, and then multiply by the subscript, which is outside those parentheses. Then you can do the rest of your bookkeeping and multiply the whole thing by that coefficient that's there. So let's break this one down and actually do it. First thing we're going to do is count the atoms in the parentheses first and then multiply by that subscript. So here we go. I know I have 1 nitrogen and I have 3 oxygen, and I have to multiply that whole thing by 3, which is going to get us 12 atoms. So this portion of that formula is 12 atoms. I also have this aluminum, which is here, which is a robust 1 atom. So now I am going to get a grand total of 13 atoms before I wind up multiplying by this coefficient that is there. So now I'm going to take those 13 atoms, and of course I am going to multiply it by 4. So 4 times 13 gives me 52 atoms total. So that is the third thing we have to do, which is essentially take the total of our entire compound and now multiply it by the 4 atoms, which was our coefficient. So that's not so hard. And of course, it is now your turn to practice. So let's take these 3 compounds. They all have a coefficient and they all have parentheses in there. And let's total up the sum of the atoms. Pause the video now while you do that, and then unpause when you have an answer. All right, if you did this correctly, we should have gotten 40, 56, and 30 atoms respectively. If you made any errors on anything, make sure you rewind the video to check out where you went wrong. Otherwise, let's proceed forward. Okay, in this next portion of the video, we are going to turn our attention to naming ions, specifically naming simple monatomic cations and anions. And for this part, you are going to need your periodic table. So make sure you grab that and have that handy. So let's review a little bit. You guys should at this point understand that a cation is a positive ion which has more protons than electrons, giving it a net positive charge. You should also remember that in order to predict the charge that a cation will take, you got to go to your periodic table and you need to look at the oxidation states that are listed there. If you look at the oxidation state, it will always tell you the ionic form of that particular atom. So that is in every single box on your periodic table, and having that information is certainly handy. So how would we name the ion? Well, if we take a lithium atom, for instance, let's go to atomic number 3 and look. Here's a lithium atom. A lithium atom takes a +1 charge and would be called a lithium ion. A scandium atom would form a scandium +3, and that would be called a scandium ion. You will notice that they simply take the element's name and the word ion, and really the name of it does not necessarily reflect what the value of the charge is. That's because there is only one possible value of the ion, so you don't have to note what the ion's charge is. How about something like gold? Well, if we look at the box, we see gold, wait a minute, could be a gold +1 or a gold +3. What's unique about gold is it is a transition metal with multiple oxidation states that are possible. If we look down here, we can see a lot of these transition metals will have multiple possible charges that are listed. And when you can form multiple possible ions, you are called a polyvalent, poly meaning many, metal. And so your transition metals tend to be polyvalent. Yes, there are some that have only one possible charge, but many of them, because of their D sublevel, which we can get into later, has the ability to have multiple possible charges. So in terms of naming a transition metal with multiple oxidation states for its ionic form, what we need to do is modify what we had just learned. It is not enough to just say gold ion, but we have to note now the charge of the ion that is present. So for instance, if we had gold +1, what we're going to do now is use Roman numerals in parentheses after the name of that particular element which turned into an ion to note the value of the ion's specific charge. So as we said before, a gold +1 would be a gold 1 ion. The 1 here in Roman numerals means that the ionic form is +1. The other ion gold could form as a +3, and if it did form a +3 ion, we would have to, in order to name it, use a Roman numeral 3 to note the +3 value of the charge. Something like manganese, which has 4 possible charges there. Let's say we had a manganese 7 ion. If we wanted to name it, we would then use a Roman numeral 7 to note the +7 of the charge. So, repeat, the value of the ion's charge is represented by the Roman numeral. And for all of you playing along at home, if you did not study Roman numerals, make sure you get this chart down here, at least the left-hand side of it. Don't worry so much about the right-hand side, but you do need to know Roman numerals 1 through 10 and their symbol. So now it is your turn. Look at the periodic table in order to decide if your ion needs a Roman numeral. Remember, it only needs one in the name when there are multiple possible charges. So you should pause the video now, have your periodic table handy, and write the complete name of the ion, inserting a Roman numeral in parentheses if your ion has more than one charge in the periodic table box. So pause the video now and do that, then unpause when you're ready for the answer. All right, if you did this properly, you will see that there are only a few ions that did not need a Roman numeral. We have the calcium ion that's there, rubidium, sodium, beryllium, and aluminum. What they all had in common was only one possible ionic state if we looked at the periodic table. And because there's only one possible charge, we didn't need to note what the charge was with a Roman numeral. The next segment that we're going to do is all about naming anions. And anions are different than cations, but in my opinion, they are easier. If you recall, an anion is a negative ion, and those are formed by the elements that are usually all the way on the right-hand side of the periodic table, which are your non-metals. So how do we name an anion? Well, what we're going to do is take the original name of the element, and then we are going to drop the ending, which we call the suffix of that element, usually the last 3 letters. And we're going to replace that suffix with "ide" and ion. So for instance, if we have a fluorine atom, fluorine, our suffix would be "ine," and then we would now, when it becomes an ion, add an "ide" and drop the "ine" and then add the word ion. So we get a fluoride ion. And obviously fluoride must sound pretty familiar because that is what all your dentists talk about, that is present in your toothpaste and all that jazz. All right, now it is your turn. Here are 5 examples of anions for you to name. So pause the video now and then unpause when you are ready for the answer. Okay, if you did this correctly, here is what you should have gotten. Remember, to name an anion, you are really dropping the last 3 letters of the element name and adding "ide" and ion. So it is a little different than cation, so be careful. All right, now let's go back the other way. Here are some anion names. You are going to write the formula and the charge that you would see given the name. And remember, anions are unique. They are going to use the most common charge that is listed on the periodic table, and that will be the one that is listed first, which generally reflects how many electrons would need to be gained in order to reach the stable octet. So pause the video now, write the formula and the charge of the ion, then unpause and check your answers. Okay, if you did it correctly, here is what you should have gotten, and you will notice, as we said before, that the first charge is the most common form of the ion, and that is the one that we are using. Before we leave this video, it would be irresponsible of me to close it out without reminding you about your polyatomic ions. Remember, your polyatomic ions are on table E, and they are ions that are composed of more than one atom. So many of them look like neutral compounds, but the truth is they're not. They're kind of like charged compounds, because you'll notice that each of them will have a charge that's here. And the value of the charge varies based on the atoms that are bonded together. We're going to cover a lot of that when we get into bonding, but in the meantime, for now, it is all about memorizing the formula, the name, and the charge to be successful. To help you do that, there are some patterns in naming when you are dealing with all your ites and your ates. So there are lots of oxyanions, or what they call oxoanions, that are on here. These are basically polyatomic ions that have oxygen as a major component. And you will notice many of them end in ite and some of them end in ate. So let's talk about the differences between ite and ate. Basically, if you have a family of polyatomic ions, and here are some of your families you'll see. We have sulfur-based, nitrogen-based, chloride-based, phosphorus-based. When you are looking at the formulas that are here, the greater the number of oxygen in the family, that usually is the polyatomic ion that takes ate as its suffix. So for instance, here we see SO4 would be sulfate, NO3 would be nitrate, ClO3 would be chlorate, and PO4, 3- would be phosphate, while the polyatomic ion with fewer numbers of oxygens would get an ite suffix. So if SO4 was sulfate, SO3 is sulfite, NO3 is nitrate, NO2 is nitrite, chlorate, chlorite, phosphate, phosphite. Remember, this does not have to do with the exact number, but it has to do with a comparison between the two members of the family, and the one that has the greater number of oxygens gets the ate versus the ite. So that just might be something to help you along while you are trying to memorize these polyatomic ions. There's more that are in there, and obviously the only way to get through this is to put the time in, make yourself a Quizlet or flashcards, and just bang it out. So that is it for me. We have gotten through counting atoms in your formulas and naming your ions of all different types. If you do have any burning questions, make sure you please bring them to me in the burning questions segment during our next session. It has been a pleasure taking you through our first lesson in nomenclature. We gonna see you on the flip side. Peace out.
That's all, folks.